Welcome to TalkTensors, your deep dive into machine learning research. Today we're tackling a really interesting paper looking at a new way to model what's beneath the Earth's surface using neural networks.
That's right. It's focused on 3D magnetotellurics, or MT, which is a key geophysical method. And this paper introduces a specific architecture, MTAG-Net, to handle the forward modeling part.
Right, the forward modeling that's basically predicting the electromagnetic response based on a given subsurface structure.
Exactly. And the big challenge there has always been, well, computation. Traditional methods like FEM or FVM, they get really slow and memory hungry for complex 3D scenarios.
Yeah, I can imagine. Trying to simulate all those electromagnetic fields in 3D. It sounds intensive.
It really is. So this paper is trying to, leverage deep learning to bypass a lot of that heavy computation.
And the core innovation they're proposing is this thing called MTAG-Net, which uses an attention gating mechanism. Sounds fancy.
It is pretty neat. The AGU part stands for Attention Gated UNet. The idea is it helps the network focus more effectively on the important parts of the input data, the resistivity model when it's predicting the output, which is the MT response.
Okay, so it's like giving the network smarter eyes to see the crucial geological features.
Sort of, yeah. It helps weigh the information coming from different parts and depths of the model. So for you listening, this could mean faster, maybe even more accurate ways to map out things like mineral deposits or understand deep earth structures.
All right, sounds promising.
Yeah.
Let's dig into the paper itself. How does this MTA-UNet actually work?
Okay, so fundamentally, it's built on a 3D UNet architecture. If you're familiar with UNets, they have this encoder-decoder structure, right? Like a U shape.
Yeah, compressing the input down to capture features, then expanding it back up to create the output map.
Precisely. And they use skip connections, these links between corresponding layers in the encoder and decoder.
Those are important for keeping the fine details, aren't they? So the network doesn't forget the specifics as it gets more abstract.
Exactly right. Now, MTAG-Net puts this special dual-path attention gating module within those skip connections. That's the key addition.
Okay, so the attention isn't just tacked on, it's integrated right into that information highway between the encoder and decoder. What does this dual-path attention do?
Well, it cleverly uses information from the deeper, more processed features in the network. Think of those as understanding the broader context to guide how the network uses the shallower, more detailed features.
Ah, I see. So the deep features help the shallow features know what's important.
Kind of, yeah. It uses spatial attention, focusing on where important changes are, like resistivity, boundaries, and also channel weighting, figuring out which types of features matter most at that location. It essentially learns to amplify signals from those really critical zones where conductivity changes sharply.
That makes sense. It's trying to mimic how an expert might focus on specific anomalies. But neural networks need a ton of data to learn this, right? Especially for complex 3D stuff. Where did they get it all?
That's a really critical point they address. They couldn't just use real-world data. There isn't enough labeled 3D data like that. So they generated synthetic data. But importantly, they used something called 3D Gaussian Random Fields, or GRF.
GRF. Okay, What does that give them that, say, putting simple blocks underground wouldn't?
It allows for much more realistic complexity. Instead of just sharp, blocky interfaces, GRF can create smoother, more continuous, and sort of statistically structured variations in conductivity, things that look a lot more like actual geology. They generate, I think, 10,000 of these complex 3D models.
Wow, 10,000. And for each one, they had to figure out the correct MT response to train the network.
Yes, and that's where the traditional methods come back in, but just for data generation.
Wow.
They used a Finite Element Method, FM solver, to calculate the MT response for each of those 10,000 GRF models. That took time about 2 minutes per model, they said.
Okay, so they invested the computation up front to build a really good, realistic training set.
Exactly. High-quality synthetic data is key here. Then they trained the MTAG-Net to learn the mapping from the GRF resistivity model to the FEM calculated response.
And did it work? How did it compare to, say, a standard 3D UNet without the fancy attention gates?
Yeah, they did that comparison directly. The results look pretty good for MTAG-Net. It showed more stable convergence during training, meaning it learned more smoothly.
Okay, smoother learning is good. What about the actual prediction accuracy?
That's where it really seemed to shine. They used metrics like root mean squared error, RMSE, and also the structural similarity index, SIM. The SIM is interesting because it measures perceptual similarity, not just pixel by pixel error.
Right, so it tells you if the predicted map looks like the true map, capturing the important structure.
Precisely. And MTAG-Net consistently got SIM scores above 0.98, sometimes even 0.99 on the test set. The standard UNet was lower, maybe around 0.96, according to their examples. You could visually see fewer artifacts and sharper details in the MTAG-Net predictions.
That's a noticeable difference. So the attention mechanism seems to be genuinely helping it capture those critical conductivity variations.
It seems so. The trade-off was training time MTAG-Net took longer to train, maybe 21 hours versus 16 for the standard UNet in their setup, because the attention module adds computation.
But once trained, the prediction is super fast.
Yeah.
Compared to running FEM every time.
Oh, absolutely. That's the whole point. Once trained, the network can make a prediction in seconds or less, whereas FEM takes minutes or hours. We're talking orders of magnitude faster for inference.
Okay, that's a huge practical advantage. Did they test how much data they actually needed? Like, do they need all 10,000 samples?
They did look at that. They trained it with different data sizes, from 1,000 up to 10,000. As you'd expect, performance generally improved with more data, but they saw diminishing returns. It looked like around 6,000 samples might have been a sweet spot, kind of an elbow point in the performance curves.
Interesting. And what about robustness? Real-world data is noisy.
Good question. They tested that too, adding Gaussian noise to the input resistivity models. MTAG-Net seemed pretty resilient up to about 5% noise, maintaining decent accuracy. Performance dropped off more significantly at 10% noise, which isn't too surprising.
Still, some robustness is good. And generalization. Could it handle types of structures it wasn't explicitly trained on?
They tried that by testing it on models that combine the smooth GRF backgrounds with sharp, blocky anomalies, embedded within them something different from the training data distribution.
So, discontinuous structures.
Right, and it actually generalized pretty well. The predictions still captured the main features, even if there were some minor deviations around the complex anomalies. The SIM scores remained high, suggesting it learned the underlying physics reasonably well, not just memorizing the training patterns.
Okay, that's quite comprehensive. So, stepping back a bit, how does this fit into the history of trying to solve these kinds of problems?
Well, as we touched on, MT itself isn't new. People have been using natural electromagnetic fields to probe the Earth for, 70 years or more.
Wow, okay.
But modeling it accurately in 3D has been the long-standing challenge. First came analytical solutions for very simple 1D cases. Then, with computers, came numerical methods. Finite difference, FDM, was early on, then finite volume, FEM, and finite element, FEM. It became very popular for handling complex geometries.
It all struggled with the computational cost for large 3D models.
Hugely, especially as people wanted higher resolution and larger survey areas. So for decades, there's been this trade-off between model complexity and computational feasibility.
And that's where deep learning enters the picture more recently.
Exactly. Over the last, say, 5-10 years, there's been growing interest in applying deep learning to geophysical problems, specifically to tackle these computational bottlenecks. Early successes were often in 1D or 2D MT or other geophysical methods like seismic imaging.
So this paper is pushing that trend into the challenging 3D MT forward problem space.
Precisely. It's building on earlier work using UNets for geophysical tasks, but adding this refined attention mechanism specifically tailored for the complexities of 3D MT data, where relating surface measurements to deep structures is tricky. And the GRF data generation is also a key methodological contribution for training these models effectively.
Got it. So key takeaways seem to be: traditional 3D MT modeling is slow. MTAG-Net offers a potentially massive speedup for predictions once trained. The attention mechanism is crucial for its improved accuracy by focusing on key features. And realistic synthetic data using GRF is vital for training.
That sums it up pretty well, and the good generalization that suggests it might actually be useful in practice.
Which brings us to real-world implications. What could this mean down the line?
Well, the most obvious one is speeding up exploration surveys for things like minerals, geothermal energy, or groundwater. Faster modeling means faster interpretation, potentially reducing project timelines and costs.
Could it lead to more accurate mapping, too?
Potentially, yes. If the model is more accurate, you get a clearer picture of the subsurface. This could be important not just for resources, but also for, say, understanding complex fault zones, for earthquake hazard assessment, or mapping magma chambers beneath volcanoes.
And you could even imagine, maybe, near real-time analysis in the field if you could run the trained network on portable hardware.
That's definitely a possibility down the road. Deploying trained networks for rapid field assessment is a very attractive prospect, and the GRF method they used for data generation could be adopted for training networks for other geophysical problems too.
Okay, lots of potential impact. Now let's shift gears to our novel notions segment. Based on this paper, what's a cool, maybe slightly out there research idea it sparks?
Okay, here's one. We talked about the attention mechanism being data-driven, right? It learns what to focus on from the training examples. What if we try to make it physics-informed?
Physics-informed attention. How would that work? You mean baking Maxwell's equations into the attention module somehow?
Sort of, yeah. Or at least the principles. Instead of letting the network figure it all out from scratch, we could encode some knowledge about how EM fields should behave, like maybe design the attention gate to inherently give more weight to regions with strong conductivity gradients, because we know physically that's where scattering and secondary fields are strongest.
Interesting. So you'd be guiding the network's learning with known physics.
Exactly. This could potentially make it learn faster, require less data, or maybe generalize even better, especially to situations really different from the training data. It could also make the attention maps themselves more interpretable, you know? If the network focuses where physics tells us it should focus, we'd trust it more.
Yeah, that addresses the black box issue people often raise with deep learning, making it less of a black box and more grounded in first principles. I like that. What's another notion?
My second one is about hybrid modeling. MTAG-Net is super fast for prediction, right? But maybe traditional FEM is still, the gold standard for ultimate accuracy in a very specific spot if you need it.
Okay, so how do you combine them?
What if you used MTAG-Net as a rapid screening tool? Run it over a huge survey area very quickly to get a first-pass 3D model. Then use that result to identify just the small, specific zones that look most interesting or complex.
And then zoom in on those zones with the slow, high-precision FEM.
Precisely. You'd use the deep learning model to guide the application of the computationally expensive method. It's like using a wide-angle lens first, then switching to a telephoto for the important details. You get the speed benefit of AI for the bulk of the work, and the targeted accuracy of traditional methods where it counts most.
That sounds very practical, actually. Leveraging the strengths of both approaches seems like a high probability path forward.
I think so too. Hybrid methods are becoming increasingly common in computational science.
Really fascinating ideas. And just a quick reminder for everyone listening, these novel notions are just us brainstorming fun speculation, not proven research yet.
Absolutely. Food for thought.
So wrapping up this deep dive, the MTAG-Net paper presents a compelling case for using attention-boosted deep learning in 3D magnetotellurics. It's a significant step towards making these powerful geophysical methods faster and potentially more accessible.
Yeah, the combination of the advanced architecture and the realistic data generation strategy really pushes the envelope. Definitely check out the paper if you want the full technical details.
And it leaves us pondering that bigger question. How do we best blend the pattern-finding power of AI with the fundamental physical laws we already understand? Finding that synergy seems key to the future of scientific discovery.
Well said. It's an exciting time to be working at that intersection.